cross-flow heat exchanger. The hot flue gas comes out from here with high temperature, contact with the coolest gas get in. In the situation, it's better in this situation because the temperature is low, it's better to consider convection. But here we have a high temperature, the radiation is the most important phenomenon for heat transfer. But we have to consider this one. In this section, we have a temperature, enough temperature difference in this section, and here is not important the temperature, just radiation, the temperature for contact, because we neglect this temperature as a zero. You know, it's the temperature used by power of 4. By power of the temperature here is above 1,300 degrees centigrade. If you compare it with the gas comes into this section by temperature maybe 150, maybe less than 100 degrees centigrade. If you move them to power of 4, this one, you can see, you can ignore this one. Because of this matter, the radiation is very important. You can calculate this equation, but it is 1,300 minus 100, that means 1,200. This equation is very low. And when you compare this one with the Stefan Boltzmann rules, you use this, you multiply 1,300 4 times to itself. You have a very large number. Maybe this is less than 1-2%. It's very smaller than radiation. In this situation, it's better to consider the most important heat transfer phenomenon in the system.
Sorry, Mr. Ali.
Yeah.
I have a question regarding the FG.
Fuel gas.
Yes, I know.
Yeah,
But that inlet in this two. Okay.
We have
The
low pressure
function,
fuel
what
gas.
The benefit of it.
The fuel gas?
No, not the fuel gas. This the two.
These are burners. You have to completely mix the fuel gas with the enough air, maybe excess air, to sure about full mixing all the molecule of fuel gas contact with enough oxygen and burn in this section. If you have insufficient air over there, maybe some part of your fuel gas convert to carbon, sitting in around, inhibit of radiation, and fouling happen in this section, and also polluted the environment. You have to give it enough oxygen to have completely burning stoichiometry. We always work over stoichiometry. We have an oxygen sensor in the stack and want to say always the oxygen here about 11%. You know, the oxygen comes here from the air is 21% and the oxygen get out is 11%. We give enough, we give excess air to the system to show about to completely burn this fuel gas in this section. It's very important to complete burning order. Because if we have complete burning, we can achieve to this temperature. If we have insufficient air in the system, the temperature cannot increase more than 900. If you power it this 40 degrees centigrade up to power of 4, you can see the major of heat transfer loss in this section.
Isn't it better to put the refractory above the temperature zone so we can have two areas that overvect on the inlet of the gas?
No. Well, you want to locate the refractory here?
No, above
convection zone.
Yes, above the
we have the three section of. I just draw off the fundamental of furnace. We have three section here. We have two section here. We have a lot of things inside of the system. We have a lot of adjustment here. We have pilot here. We have a register air on the bottom and this dampener on the top. All of this should check and adjust by your hand, but you can control this one from distance.
Yes.
It has a lot of parameters to check. Reduce of this gas, increase of this gas, and the ramp up also is very important. You cannot suddenly put into the service the furnace and line up at first. You have to line up the fuel gas completely into the system. Sure about that one, because if you have not flow of regen gas or process gas in the system, hot spot happen here. The temperature of the tubes get very high, and you see the hot spot. The structure of the tubes totally destroyed. Yeah.
Yes.